Section 14 deals with issues related to the second law of thermodynamics. Section 13 kind of revolved around the first law. First law involves energy, which is a concept we've been talking about a lot right along. Energy is a concept with its roots in mechanics. Basically, it means the ability to do work. The second law deals with a concept called entropy, which actually, when you get down to what it really means, has its roots in probability and statistics. But let's start out with with the original 19th century definition, back when the second law of thermodynamics was just about thermodynamics. Entropy, which we will use the letter S to stand for that for no apparent reason. For a reversible process, the change in entropy of a system is the heat added divided by the temperature. For an infinitesimal change, to get for some finite change in the state of a system. And a system, once again, just like in the previous unit, typical example would be the gas in a cylinder. Although we'll run through some examples and there'll be other things. You integrate from the initial to the final state. The heat added over the temperature. So if the temperature is changing as you add the heat, you have to take the entire process and divide it up into lots of little pieces, and it's the usual story. You have to sum it up. So as far as what's meant by the word reversible, well, I'll get back to that when we're further into this a little bit, but just to kind of start out, a reversible process is one where the system can get back to its original state without any outside help. Like, if you've got the usual cylinder that we're talking about here with a piston in it, if you come along with your finger and you push down on that piston, then to return it to its original state, all you have to do is take your finger off again, and that compressed gas underneath there would push the piston back up where it came from, and that would be a reversible process. Whereas if you had a little valve you could open up and you let the air escape, then the piston's going to go down and you're not going to get the piston back up without pumping the air back in, which requires some energy. So that's kind of sort of what I mean by reversible, and I'll get a little more specific about that. But anyhow, this is the original thermodynamic definition of entropy, but the more general, well, there's a whole couple of paragraphs about here. More generally, entropy measures how randomized or disordered a system is, whether that system is a collection of gas molecules like I was talking about here, or whether it's any of a lot of other things. The more fundamental definition is, it's kind of buried in a paragraph here. Let me write it out where you can see it. Put it in parentheses because we're not going to use this for anything. This is just some background information. NK natural log of N would be the number of particles in the system. K is Boltzmann's constant, and W is, as it says in the paragraph here, that's how many ways there are of arranging the system that give you the state you're talking about. So as a simple example, like it talks about here, let's, you know what, instead of looking at my hands all the time, make you feel like you're being talked to by a human being for a few minutes. So let's say you had a shoebox with 100 pennies in it. And the state of the system that we want to talk about is how many heads and how many tails you've got on those coins in that shoebox. Now, having 100 heads and no tails is a state with a very low amount of entropy, because there's only one way of arranging the pennies that does that. Whereas having half heads and half tails is a state with a much higher entropy, because there are many, many ways of arranging the pennies that gives you that. I mean, even 99 heads and one tail, there's 100 ways of getting the pennies. Because if you start out with all heads in there, and then you want to go to 99 and one, well, you could turn over this penny, or you could turn over that penny, or you could turn over this penny. There's 100 different ways of getting 99 and one, which makes it, if you shook up the pennies, put the lid on, shake it up real good and see what you get. Since each way of arranging the pennies is equally likely, getting 99 and one is 100 times as likely as getting all heads, because there's 100 times as many ways of arranging the pennies that gives you that. Well, by the time you get to, after you've had 100 choices as to which penny to turn over first, if you're going to talk about 98 and 2, your 100 choices is followed by 99 choices as to which one you're going to turn over next. By the time you get to half heads and half tails, there's a lot of ways of arranging the pennies that give you that, which is the reason why if you put the lid on the box and shake it all up, you will almost certainly get roughly half heads and half tails. Maybe it'll be 49 heads and 51 tails or something like that, but it'll be somewhere in that neighborhood. Getting all heads is not impossible. It's just extremely unlikely, because there's only one way of arranging the pennies that gets it. And, it's anyhow, I think you see how the probabilities would work out there. The second law of thermodynamics is ultimately a statistical thing, okay? So that kind of illustrates the basic principle of the second law. Systems migrate toward more randomized states simply because they are more likely. Having the pennies more mixed up is just much more probable than having them all heads. So entropy actually, when it comes right down to it, has to do with, physicists have their equation for entropy, which I wrote there, the one with the natural log of how many ways there are of arranging the system. Interestingly, that is almost exactly the same equation that the information science, the computer science people have for the information content of a system. There's a few little differences, like the computer science people, I guess, like to use a log to the base 2, or physicists are kind of fond of log to the base e and things like that. But ultimately, what entropy is telling you is how much information you have about a system. Because if you have 100 heads and no tails, you know what's going on with every single one of those pennies. You have a lot of information about the pennies. Whereas if all I tell you is that it's half heads and half tails, well, for any given penny, you don't know if it's heads or tails. If I start telling you, well, this one's heads and this one's tails and this one's tails and this one's heads, if I give you that amount of information, well, now I've narrowed it down to a state, which is just as specific as saying it's all heads. And that would be just as unlikely as getting all heads is. So anyhow, that's what entropy is. Okay, is it describes how randomized the system is, or ultimately how much information you know about the system. And systems tend to migrate toward states of greater entropy because they're more probable. Now, applying that to heat flow, because after all, this is supposed to be thermodynamics I'm talking about. I mean, that general definition of entropy, this general way of stating the second law that is in the middle of the page here. Second law of thermodynamics, delta S greater than or equal to 0, and in parentheses it says entropy does not spontaneously decrease. You're not going to get a deck of cards and start shuffling them, and when you're done, find out you've got 2 of clubs, 3 of clubs, 4 of clubs, 5 of clubs, 6 of clubs, and so on. Not that it's impossible, it's just extremely unlikely. Well, stated in that form, the second law has very wide-ranging implications, from information theory to, you name it. But if you want to focus in on thermodynamics in particular, what it means is that heat flows spontaneously. You can pump it the other way, but heat flows spontaneously only from hot places to cold places. In other words, you are not going to put a pot full of water on a hot stove and then watch it freeze. Now, just like shuffling the cards and having them all turn out to be in order when you're done, it's not, strictly speaking, impossible. I mean, in practical terms, it's impossible. But, you start talking to a mathematician and you say, well, the probability of this is something like 10 to the negative 250th power. And a mathematician would go, that's not 0. Yeah, but if you turned all of the matter in the observable universe into stoves and pots of water and watched it, since you would have to watch it for 100 times the present age of the universe to see it happen just once, okay? And if you ever do put a pot of water on the stove and watch it freeze, if you just happen to be in the right place in the right time, you're in that one spot in the whole history of the observable universe, which is a big place. And yeah, don't bother telling anybody about it, because they're not going to believe you. And it's not like you can tell them, no, come over to my house, I'll show you, I'll do it again. No, when you do it again, it's not happening. So if you have a hot stove and a pot full of cold water, the thermal energy is unevenly distributed. Just like if you had 10 heads and 90 tails in the shoebox, that's unevenly distributed, okay? So you shake it up, and the word spontaneously is important because you can reach into the shoebox and turn over some of the pennies and make them all heads that way. But if you just shake it up to see what happens spontaneously, things tend to even out, okay? The pennies in the shoebox are going to migrate towards half heads and half tails. If you pour some milk in a cup of coffee, even if you don't stir it, eventually the milk is going to diffuse around throughout the cup of coffee. That's the second law also, okay? The second law says things tend to even out because that's the most randomized state. So if you got a hot stove and some cold water, where the thermal energy is located tends to even out. And that means that some of it will move into the cold water until everything reaches a uniform temperature. Okay, so the second law, as applied to thermodynamics, a little further down the page here, second law restated, heat doesn't spontaneously flow from a low temperature to a high temperature. So that's kind of the idea. That's what entropy means. It's how randomized the system is, at least when you look at it on a fundamental level. But now we've got some more stuff to write, which you would prefer would be right side up, I imagine. And yeah, that looks pretty straight like that, I guess. Delta S for an ideal gas. Well, let's consider, as usual, just an infinitesimal change in the state of a system. The little bit of internal energy that's added in this infinitesimal change would equal the heat that's added plus the work done. That's the first law. Well, you see, what I need is I need an expression for dq to put in this. So I'm going to get my dq out of this, and then I'm going to stick it in that and integrate it, and that'll give me a formula for the entropy change for an ideal gas, like it says in the middle of the page there. So solving it for dq. You've got that. Well, from section 13, the change in internal energy during any kind of process is equal to N times CV times the temperature change. And also from section 13, the work done as a gas expands. Well, actually, if it's the work done on the gas, I guess you'd be compressing it. Well, either way, it's given by minus PdV. So I'm going to recopy the first part of that. Minus cancels minus. And then substitution for the pressure from PV equals nRT. P is equal to nRT over V. So there is a not exactly compact expression for the amount of heat added. Plugging that into this definition for delta S, well, N and CV, those are constants. And right now, this is, I'm going to, sum of the integral of a sum is the sum of the integrals. So I'm going to have one integral for this term, and then I'll have a plus sign, and I'll have another integral for this term. So right now I'm doing this. And remember, it's divided by t. So delta s is all of this divided by t. And so that's where the t that's underneath the dt came from. It came from here. And on this term also, there are some constants I can, oh, I suppose I should put the limits of integration on here. Initial state to the final state. Again, this has to be divided by t to get the entropy. So I'll have t over t, and then from here I'll have, of course, the t's cancel out. So there's just logarithms all over the place. And I'm going to kind of combine a couple of things here. You evaluate at the upper and lower limits. So you'd have the log of t final minus the log of t initial. And then the difference between the logs would equal the log of the quotient. So log of t final minus minus the log of t initial would be the log of t final divided by t initial. So delta s NCV log of t final over t initial plus so that's for an ideal gas. If a question asks you to find the change in entropy of, you know, a cup of water or something like that, this would not apply. But you know, because like right here, I used the ideal gas law as part of its derivation, so it's only going to be valid when PV equals nRT. You'll find this is on your formula sheet. I mean, this kind of thing is what a formula sheet is for. Even I don't have this one memorized. So anytime it's an ideal gas, anyhow, you can throw the numbers at that. And that's where it comes from. What's further down the page here? Example. So we've got some ice at the melting point, 0 degrees, placed in an insulator. The volume doesn't change, and there's helium gas in there, which is several degrees warmer than the ice. As the gas cools down to 0 degree, everything's going to end up at 0 degrees. Okay, what happens is that as the helium cools off, the heat lost by the gas goes into melting the ice. Okay, it provides the latent heat of fusion to make 0 degree ice into 0 degree liquid. So if you wait long enough, which will probably take a while actually, but if you waited long enough for everything to reach thermal equilibrium, there's enough ice there that it won't have all melted. There's more than 50 grams of ice in the container is the idea, but 50 grams of it is how much melts by the time the helium is cooled off to 0 degrees and can't melt any more ice after that. So change in entropy of everything inside this container. That would be the total for the ice and the helium. So we have to calculate delta S for the ice, we have to calculate delta S for the helium, and then add them together, and that would be the entropy change for the entire system. Now for the helium, that's going to be this thing that I just derived here. For the ice, well, for the ice, we're going to go back up to this. Okay, so that's kind of the general plan of attack. Details go like this. Oh, I don't like that. It's got some kind of rust marks on it. That one looks better. Let's see, I called this number 1. So it looks like I did the ice first. Delta S is the integral from initial state to final state of dq over t. Now, what makes this, what simplifies things for us in this case is that the ice does not change temperature. It starts out at 0, well, of course, actually, T would represent the Kelvin temperature, just like it always does. So instead of saying 0 degrees Celsius, maybe I should call it 273 degrees Kelvin. But anyhow, it starts out at 273, it ends up at 273. It's a constant, which means we can take it out in front of the integral, which means we're going to have a really simple integral. If you don't know how to do the integral of dq, you have just not been paying attention in calculus class. So 1 over t, initial to final, and again, I can take it out because it's a constant, 0 degrees Celsius. Because the temperature is constant, I can treat it like a constant. So Q final minus Q initial, if you want to think of it that way, delta Q. So it's just going to be the heat added divided by the temperature of the ice as it received the heat. Well, from Physics 131, the heat added to ice as it melts is its mass times the latent heat of fusion. Okay, so Physics 131, Q equals the mass times the heat of fusion. Numbers to fill in. We have 50 grams of ice that's melted, 0.05 of a kilogram. And the heat of fusion. Well, this is not something we use too often in this course, so you won't find it on your formula sheet for this course. So like if a question like this came up on a test or something, I'd have to provide you with this number in the question. But it is on your, if you still have your formula sheet from Physics 131, it is in there, and that's where you could get this from. Measured in joules per kilogram. The heat of fusion of ice is about 333,000. The temperature, 0 degrees Celsius, it's 200. I'm going to go a couple extra decimal places here because it turns out that you need to do that in the end. So carrying plenty of decimal places and assuming that these other numbers are also good to many significant figures, which is almost certainly not true for this, but that comes out 60.99. That would be measured in joules per Kelvin, units of heat divided by temperature. Okay. Oh, that's not the answer yet. Shouldn't make it look like the answer, but that's a number we're going to want to get back in a minute. But first I have to get delta S for the gas, the helium. And that, as I said, that would be dropping numbers into that thing that I derived a few minutes ago. Once again, that was delta S equals NCV log of T final over T initial plus NR log of V final over V initial. Now, the question says the container keeps a fixed volume when all of this is going on. Constant volume means that you're taking the natural log of 1. Well, any kind of a log of 1 equals 0, so that wipes out this term. Filling numbers into the other term, said there's 100 moles of helium. That was given in the question. The constant volume molar specific heat for helium is something you can, that's one you can look up on this semester's reference handout, 12.5 for helium. It's a property of the type of gas. I don't know why I put the unit on that when I didn't put up, might as well make them match. This is in moles. So you can see what's going to happen to the units. Moles will cancel moles, and it'll come out in joules per Kelvin, which would be the unit for entropy. And final temperature is 0 degrees Celsius, 273.15 degrees Celsius, or Kelvin. And the initial temperature, that was 13.37. You add this to that number, and you've got 286.52 kelvins. So kelvins over kelvins leaves you with a dimensionless number. You always, logs or trig functions or anything like that, the argument has to be a dimensionless number. And then times these things. Anyhow, this part of it here, the logarithm is negative 0.0477787 or something like that, times the other two numbers, and you get negative 59.73 joules per Kelvin. So this is the entropy change of the ice. Since it was gaining heat, that gives it a positive entropy. This is the entropy change of the helium. Since it was losing heat, that gives it a negative entropy. So the delta S for the entire system $60.99 minus 59.73, and we've got 1.26 joules per Kelvin. That's the answer. That is how much the entropy of this mixture of gas and ice changed as the ice melted. Now, maybe and I think this is written out on the, yeah, as I actually wrote right out on the handout here. Maybe the most significant thing about this answer is not that it's 1.26 as opposed to 1.43 or something like that, but simply the fact that it came out positive, because there's the second law back up there. The second law allows things to happen spontaneously if the entropy change is positive, and it prohibits them if delta S is negative. Well, this came out positive, so this is something that can really happen. You see it every spring. You got snowbanks all over the place, and you get a nice warm day where the air is 40 or 45 degrees or something, and it melts the snow, okay? And that's pretty much what's going on inside this container, except it's helium rather than air. But that's perfectly allowable. If you consider the reverse process, okay, what if you started out with a well-insulated container that had a lot of water in it and some helium, and everything was at 0 degrees Celsius? And then what happens next is that heat flows out of the water into the helium, and more ice freezes as the gas gets hotter and hotter. Well, that would be the exact reverse of what I just did here. It would be the exact same calculation, except initial and final would be switched, okay? So like here, the 273 would be on the bottom and the 286 would be on top. You'd have the same number, but with a plus sign. And in the same way here, if the heat was flowing the other way, this would be negative, and it'd make the answer come out negative 1.26, which says the second law does not allow that to happen. It's not going to let heat flow out of the 0 degree water into the 13 degree helium that's around it spontaneously. Heat does not flow from cold places to warm places spontaneously. So notice that delta S came out positive, meaning that the entropy increased. This means the second law allows this to happen. Reversed everything, da-da-da-da-da. Okay, I've already said that. Let's talk a little bit about irreversible processes. So remember, back at the beginning here, where did I put that? For a reversible process, delta S equals that. If it's an irreversible process, the equation is not valid. So how do you handle an irreversible process? Well, let's have an example in mind. The classic example of an irreversible process is a free expansion. But I guess before I get to that, define it a little better. One way of describing an irreversible or a reversible process, if it is reversible, it has a well-defined path on a PV diagram. In other words, you've got your little graph, P, V, and maybe the gas starts out there, that much volume, that much pressure, and you're going to compress the gas until it reaches this state over here. If it's a reversible process, well, actually, let's make it an expansion. Let's do it the other way around, because that would that's what's coming up in the example. So the gas starts out here, and you let it expand until it gets there, pushing a piston outward. And at every moment in between, from when the gas started expanding until it reaches its final state, at all times, the gas has a well-defined state. I mean, At the moment when it was right here, it had that for the pressure and that for the volume. And if that's what goes on, that's a reversible process. So one way of describing a reversible process is it has a well-defined path on a PV diagram. It can be shown that delta S between two states is independent of the path taken. So, for an example of an irreversible process, let's consider a free expansion. So here's the usual cylinder equipped with a piston, and there's also some delicate membrane, like a really thin piece of plastic wrap or something like that. It's just barely able to stand up to the pressure from the gas, and it weighs very, very little. But that's keeping all the gas combined in the bottom half of the volume under the piston. In the top half here, it's a vacuum, okay? So that's the initial state of the system. Well, as I said, this delicate little membrane is just barely strong enough to hold back the gas pressure. And let's say that at some point it fails, okay? The little plastic membrane gets blown out of the way and the gas expands until it completely fills all of that space under the piston. So V final would be 2 times V initial in this example. Now, no work is done, okay? The piston didn't move, right? So if this is attached to the wheels on your car or something, it's not moving your car at all. So no work is done. Furthermore, there is no change in the internal energy of the gas. The internal energy of the gas would, well, the simplest example would be if it's helium. You don't have to worry about any vibrational or rotational degrees of freedom. It's just a bunch of little point-like helium atoms shooting around in there. And the faster they go, the higher the temperature. Well, just simply having this membrane out of the way doesn't do anything to slow them down, right? If you have some helium atom that's kind of going along like this, and if the membrane was there, it would have bounced off of it. With the membrane suddenly having vanished, it just goes straight until it bumps into the bottom of the piston. So just removing the membrane doesn't do anything to slow down the gas molecules. I said the membrane was very lightweight, so a negligible amount of work was done in throwing it out of the way when it broke. So a constant temperature means a constant internal energy, which, basically everything in the first law is zero. Nothing changes here. So how would you calculate the change in entropy for this process? Okay, in an insulated container, a gas undergoes a free expansion from a volume of V initial to V final. Find the change in entropy. Well, why don't we start out with how to do it wrong? Students always seem to be interested in how to do things wrong, judging by what their test papers look like sometimes. So I'll tell you how to do it wrong. And that would be to use that. Okay, I'll write it out. Oh, maybe I'll start another sheet of paper. Yeah, no, it'll probably fit in here. So 14.2. ds equals dq over the temperature would imply that ds, the change in entropy, equals 0, because dq, the amount of heat that flowed, equals 0. And where I'm getting the dq equals 0 from is right there in the question. In the question, it says insulated container. So no heat is flowing in or out through the walls of the container. So because it's an insulated container, dq equals 0, and therefore ds equals 0, except it doesn't, because you can't base the calculation on the actual process, because that process is irreversible. I never know whether to spell reversible with an ABLE or IBLE. I had to look. So you can't base the calculation on the actual process because it's irreversible, and the equation's only valid for reversible processes. But like it says here just above the question, to find delta S for an irreversible process, calculate delta S for any reversible process between the same two states. Because, like it says a little further up, it can be shown that delta S is independent of the path anyhow. This is in contrast to work, okay? If I wanted to calculate, I think I've mentioned this before, if I wanted to calculate the work done as the gas expands from here to here, well, the work done is the area under the curve. So if the gas expanded by this process here, more work would be done than if the gas expanded by this process, because there's more area under the curve if you do it that way. So work does depend on the path from the initial state to the final state. But that's not how it is with entropy. The entropy change between these two states is independent of the path taken. So just pick some convenient path between these endpoints, calculate delta S for that, and the answer is the same as any other way of getting from there to there. So let's consider a reversible process between these two states, because for a reversible process, the equations are valid. And as I mentioned a few minutes ago, since a free expansion does not affect the temperature of the gas, T final is the same as T initial. That suggests an isothermal process. I mean, I explained it in terms of think about what happens to the speed of a molecule, but if you want a somewhat more mathematical way of demonstrating that, delta E internal equals Q plus W. Q is equal to 0, as I already mentioned up here, the insulated container. And W equals 0 because the piston didn't move. So therefore, the internal energy does not change, which is what happens in an isothermal process. For a gas, the internal energy is proportional to the temperature. So saying delta T equals 0, saying delta E int is 0 is pretty much the same thing. So we had this thing again for the entropy change of an ideal gas. Delta S equals NCV natural log T final over T initial plus, didn't really leave myself enough space. Have to kind of squish the letters. Okay. This time it's the first term that's 0 because of the constant temperature. Okay. If we're thinking about an isothermal process, T final is equal to T initial, so you're taking the log of 1, which is 0, and that wipes out the first term. So the question didn't give us any specific numbers, it just wants a formula for it, and that would be this second term here. Delta S equals NR So you'd have to know the initial and final. Well, in the way it's drawn here anyhow, this isn't necessarily a scale drawing, but if you take this at face value, where this volume is twice as much as that volume, then V final equals 2V initial, you'd be taking the log of 2 times the gas law constant, 8 times 8.314 times whatever, you know, however many moles of gas are in there. The point is, it does not come out 0. So this is wrong. This would be the correct change in entropy, and that's how you deal with an irreversible process. And this is probably, oh yeah, it continues on the top of the next page here. Notice the process is irreversible. You can't return to the initial state without outside help. Once the gas has expanded to fill that entire volume, you can't take the volume back down to where it started without doing work. Okay, as you push that piston down, you're going to have to, you know, it'll cost you some effort. And the force times the distance, you're doing some work there. So you can't return to the initial state without outside help. Work is done if you push the piston down. There, or in terms of what I was saying about, you know, the clearly defined path. Notice there is no clearly defined pressure or volume during the expansion. You know, immediately after that membrane breaks, well, what exactly is the volume of the gas at that point? I mean, at the very instant that it broke, most of the gas molecules are still down here in the bottom half of the thing. They haven't had really a chance to move yet. As time progresses, you get more and more gas molecules up in here, but you're going to have kind of a pressure gradient and a density gradient with lots of molecules down here and not so many up here, but how many are up here will increase as time passes. But you know, during the expansion, what is the volume of the gas? There really isn't a good answer for that, and that's typical of an irreversible process. That's one way of defining an irreversible process. Same thing with the pressure. I mean, before the membrane broke, the pressure here was 0. The pressure here maybe was, I don't know, 1 atmosphere or something like that. After the membrane just basically suddenly disappears, you'll still have almost an atmosphere worth of pressure here in the bottom, but the pressure will get lower and lower as you go toward the top. So no well-defined volume, no well-defined pressure during the expansion. Once everything evens out, uh, then you've got a well-defined pressure because it's the same pressure everywhere, and so on. So I was going to stop anyhow, and the phone is ringing. See you in the next recording.